Welcome back to the Foundry by Forge College. I'm absolutely thrilled you're joining us again. In our previous explainer, we covered some really elegant ground with Merkle trees for state commitments and scalability. We looked at how to take these massive, sprawling amounts of data and compress them down into a single, tiny, verifiable hash. Pretty cool, right? But today we're flipping the script. We're putting on our security hats and asking an absolutely crucial question. How do we actually secure these structures against real-world threats? So, welcome to our explainer on security properties and verification strategies.
Okay, let's dive right into this blueprint. Today, we'll be looking at the limits of Merkle trees, diving into cryptographic versus operational trust, and exploring common attack vectors. Then, we'll build our cryptographic defenses, implement operational security strategies, and finally, wrap up by securing the root.
Section 1. The limits of Merkle trees beyond the math. To start off, we really need to challenge a dangerous but super common assumption. It's incredibly tempting to look at a cryptographic hash function, see that the math works flawlessly on paper, and just assume your entire system is totally invincible. You picture these cartoonish adversaries trying to brute force passwords for 1 billion years. But real-world attackers, they're much smarter, way more creative, and frankly, a lot lazier than that. They look for the cracks in how the math is actually applied. And that brings us to a fundamental concept, the compound guarantee. Think of your Merkle-based system as a two-part vault. The mathematical soundness, your unbreakable hash function, well, that's the foot-thick steel vault door. But the operational trust, how the system is deployed, updated, and checked out in the wild, that's the security guard standing right next to the door. Having an impenetrable vault door means absolutely nothing if your security guard just smiles and lets an imposter with a fake badge waltz right in. We literally need both to be secure.
Section 2. Cryptographic versus operational trust. Assessing assumptions.
As engineers and architects, we have to formally separate our assumptions here. We need to separate what we assume about the hash functions happening inside the computer from what we assume about the real-world data transport and storage happening on the outside. On one hand, we've got our cryptographic assumptions. We trust that our hash resists collisions and preimages. On the other hand, we have our operational assumptions. We're trusting that the root we are checking against is authentic and up-to-date. Think about it. If you verify a mathematically perfect proof, but you do it against a completely wrong, tampered root, well, the heist was successful. The math worked flawlessly, but you still lost everything because the operational side of things completely failed.
Let's zoom in on that cryptographic dependence for just a second. A Merkle proof's basic guarantee relies heavily on two key things. First is collision resistance. This stops an attacker from finding two totally different sets of leaves that magically spit out the exact same root. Second is preimage-resistance, which prevents a bad actor from working backward from a known root to artificially craft a fake leaf that perfectly matches it. If the underlying hash function is weak or broken, the entire tree just rots from the inside out.
Section 3. Common attack vectors. Bypassing the math.
So what happens when attackers decide to just bypass the math entirely and go straight for the structure? Well, it's time to open up the playbook and look at the common attack vectors our sneaky time travelers and data forgers use to break in. Now, what's really interesting about this matrix is how it perfectly maps out the heist. Look at how every single attack is countered by a specific, concrete mitigation. For a collision attack, we fight back with domain-separated hashing. For root substitution, where they try to swap out the trusted root, we mitigate that by anchoring those roots. If they attempt proof malleation by reordering the siblings in the tree, we canonicalize the format. And for a stale root replay, where they try to pass off an old root as a new one, we lock that down with epoch binding.
Let's break a couple of these down a bit more, starting with proof malleation. This happens when forgers exploit ambiguous node ordering. Imagine a recipe that gives you all the ingredients but doesn't actually tell you the order to mix them in. If an attacker can just omit a sibling node or shuffle whether a hash belongs on the left or the right side of the tree, they can completely break the proof and trick the verifier. If we don't have a rigid, unbending structure in place, the system just cannot tell the difference between a valid proof and a cleverly shuffled fake.
Then we have the stale root replay. This is a genuinely fascinating attack where an adversary presents an old root along with a perfectly matching proof to hide a state rollback. It's exactly like walking into a convenience store and trying to cash a winning lottery ticket from 2012. I mean, yes, the ticket was real, and yes, the math and the numbers check out perfectly, but accepting it way outside of its proper time frame, that's a fatal operational failure. Timing matters just as much as truth here.
Section 4. Cryptographic defenses, code level patching.
All right, so we know how they try to get in. Let's shift into defense mode.
First up, we have domain separation. Step 1, you prefix your leaf data with a 0x00 byte. Step 2, you prefix your internal nodes with a 0x01 byte. Why do we do this? Well, a hash function is basically a meat grinder, right? It just processes whatever you feed it. Domain separation is kind of like slapping a giant neon "I am a leaf" sticky note on the leaf data, so the hash function doesn't get confused and accidentally process an internal node thinking it's raw data. It cleanly separates the domains of your data types. Next up, we defend against those shuffling attacks with canonical encoding. Here, we strictly require that the length of the position data exactly equals the length of the sibling data. Plus, we include explicit position bets indicating left or right for every single sibling in the proof. So the crucial point is that canonical formats completely eliminate the ambiguity that forges rely on. We're leaving zero room for interpretation. There's literally only one mathematically accepted way to present the proof. Section 5. Operational security. Real-world guardrails. Okay, so our cryptography might be completely locked down, and our proofs are totally unambiguous. But remember the vault. A strong door just isn't enough. I want to pause for a second and ask you a direct question. What if the math works perfectly, but the root is old? What happens when our verifier receives that 2012 lottery ticket? We need a way to pivot from just checking cryptographic math to actually checking operational timestamps. And here is our operational defense workflow to handle exactly that. Step 1, confirm the root is anchored to a trusted, timestamped checkpoint. Basically, this means we check multiple trusted sources to make sure this root is currently recognized as the absolute truth. Step 2, enforce proof freshness. We just outright roots that are older than our configured maximum age. By implementing these freshness checks in your verifier, you effectively freeze out those time-traveling replay attacks. You're essentially telling the attacker, hey, your math is good, but you're just too late.
Section 6. Securing the root, the final anchor.
Let's bring this entire architectural blueprint together. How do we secure the absolute final anchor of trust in a system that relies on countless hashes? It all boils down to this single, absolutely vital quote: cryptographic guarantees are conditional. I really want you to remember this. A correct, mathematically perfect cryptographic proof is absolutely necessary, yes, for sure, but it is fundamentally insufficient without operational anchoring. The math needs the real world to give it context, boundaries, and authority.
And this brilliantly illustrates exactly what we'll be covering in our next explainer, the foundations of digital signatures. While Merkle roots give us an incredibly efficient summary of state, digital signatures will step in to provide that operational authenticity layer. They'll act as the ultimate cryptographic security guard for our vault, signing off on our roots and verifying exactly who authorized them and when.
It really is fascinating, isn't it? We place ultimate trust in these simple hashes, but if we don't build the right operational guardrails around them, they're incredibly vulnerable. It really begs the question, what other seemingly unbreakable digital systems in your life are just one operational failure away from total collapse? I hope this explainer gave you a really clear, structured view of how to secure your verification strategies. To master the rest of your Web3 fundamentals and to explore all of our other courses and community resources, please head over to forge.college. Keep building securely, and I'll catch you in the next explainer.